In this video, we will see the magnetic field intensity due to finite length conductor. So we will consider a finite length current carrying conductor. That current is the DC current I, so which is oriented in the Z direction from height Z1 to Z2. That means lower end of the conductor is at Z1, upper end of the conductor is at Z2. And we will take the observation point is on XY plane. No need to take on XY plane, but I'm taking it is on the XY plane with coordinates rho comma phi comma 0. In the cylindrical coordinate system, we are going to solve this one. Okay, so we will take it is x-axis, y-axis, it is z-axis, and I will take the conductor is like this, and in which current I is passing. Lower end of the conductor is at the height of Z1, upper end of the conductor is at the height of Z2. And we will take a small portion differential length in the conductor, that is dz. Okay, actually that is dl, because it is oriented in the z direction. I can take dl is equal to dz. The small current element we have to define here. Current element, that is ideal. So due to this small current element ideal, we need to find the differential magnetic field at the observation point. Then we have to do integration with respect to z from z1 to z2. Then we can get the total magnetic field intensity at the observation point due to this entire current carrying conductor. That is the approach we are following here. For this, we are going to use the Biot-Savart law. So as per Biot-Savart's law, dH bar is equal to ideal cross r cap by 4 pi r square. This unit vector r cap you can write as the normal vector, that is r bar by magnitude of r. So you can write ideal bar cross r bar by 4 pi r cube. So what is the difficulty to find the magnetic fields in comparison with the electric fields? Means in the electric fields, the electric field is along the line joining the observation point and the source point. It is very simple. But in case of the magnetic fields, if you see this particular expression by Biot-Savart's law, the direction of the magnetic field is not along the line joining the observation and source. It is in the direction of dl bar cross r bar or r cap. So this is the main thing we have to focus. Okay, because some additional thing we have to do to find the direction of the magnetic field intensity, it is somewhat difficult, and rest of the thing is related to the magnitude only. Okay, now we are going to derive the expression for the magnetic field intensity h bar at the observation point, which is on the xy plane due to this particular finite length current carrying conductor. Okay, so for that I am taking the observation point on the xy plane with the coordinates rho comma phi comma 0. The source point on the conductor is given by, because it is there on the z-axis, rho value is 0. The phi value I am taking with respect to this observation point, and this source point is available at the height of z. So Z1 is the lower end of the conductor, Z2 is the upper end of the conductor. Okay, that means these are fixed values. Z1 is fixed or constant. Z2 is upper end, so it is also fixed. But Z you can take anywhere from Z1 to Z2. So it is the variable. So this clarity we should maintain. Okay. So Z is the variable. Z can be Z1. Z can be Z2. Z can be anything from the Z1 to Z2. Okay. So now just what is this R bar? R bar is the distance vector which is joining the source point and the observation point. Okay. So I'm drawing that one. So this is R bar. Okay. So I'm writing here OP is rho comma phi comma 0, SP is 0 comma phi comma Z, and R bar is equal to OP minus SP, that is equal to rho cap minus Z into Z cap. And if you want magnitude of R, that is rho square plus Z square power 1 by 2. Okay. So we are ready to substitute in the dH bar by Sauer's law. So what we will get? dH bar is equal to I, dl is dz, z cap, dl bar we have to write, that's why in the vector form I'm writing, that is dz into z cap. It is multiplied with the r bar, that is rho cap minus z into z cap by 4 pi magnitude of r cube. So that is z square, rho square plus z square power 1 by 2 is the r. It is having cube, that means 3 by 2. Now we need to perform the cross product in between these two. Okay, how that cross product is there? Z cap is in cross product with the rho cap minus Z into Z cap. Okay, so we know that rho is a constant, Z cap cross rho cap is the phi cap, and next one is minus Z into Z cap cross Z cap is 0. That means the resultant will be in the phi direction. Okay, so the magnetic field intensity will be having the phi direction. That is what we can able to understand here. So it is equal to I dz is already available, and from z cap onwards I got here rho into phi cap by 4 pi, and in the denominator we have rho square plus z square power 3 by 2. Then to get the overall magnetic field intensity, we have to perform the integration with respect to z. I is constant, we are dealing with DC currents only because we are working with the magnetostatics. Rho phi cap by 4 pi integral z changes from z1 to z, because we are working with a finite length conductor. If you want the infinite length conductor, just take z1 is minus infinity, z2 is plus infinity. Then we need to do the integration for dz by rho square plus z square power 3 by 2. Okay, so this is what we have to take. Now from the diagram, I'm taking the right angle triangle here just by connecting. Where is this observation point? On the xy plane. So if you connect like this, it will become rho. Then we have to connect the lower end towards the observation point and upper end also towards the observation point. That another diagram I'm going to draw here. See carefully. This is the conductor. This is our differential length. Okay, this is the current element we have considered. That is at the height of z. Lower end is available at the height of z1. Upper end is available at the height of z2. And we'll take the observation point on the xy plane. That is this one. This is OP indicated with rho comma phi comma 0. And this is Here we have origin. Okay, so generally we'll connect like this. This is R bar and lower end is connected, another line, upper end is also connected, another line. Now this is a perpendicular from the conductor or from perpendicular drawn towards the observation point from the axis of the conductor otherwise. So this is rho. Okay, rho is the perpendicular distance from the axis of the conductor. Now we have to define the angle. The angle between the perpendicular and the line joining from the observation point towards the conductor we have to define. So I'm taking the alpha 1 angle. I'm taking the alpha 1 angle which is in between the perpendicular and the line which is joining the lower end and the observation point. The line which is joining the lower end and observation point is this line, and perpendicular line is this one. So in between these two, the angle is defined as alpha 1. Okay, so that is alpha 1. Then the angle between perpendicular and the line, this is the perpendicular line, and another line is the line which is joining the observation point and the upper end is this line. So in between these two, whatever the angle is there, that angle we can take as alpha 2. Okay, alpha 2 is the angle between perpendicular and the line joining the upper end and the observation point. Alpha 1 is the angle between the perpendicular and the line which is joining the OP and lower end. Now, can you tell the equations for tan alpha 1 and tan alpha 2? Okay, before writing the tan alpha 1 and tan alpha 2, we will take what is alpha. Alpha is the angle between the perpendicular again and the line joining the differential element ideal and the OP. So this is alpha. Now I am writing three tan functions. Tan alpha 1 is opposite side in this particular right angle triangle. You have to observe tan alpha 1 is defined here. So alpha 1 is this one. So opposite side is this. Adjacent side is this. So opposite side is Z1 minus 0 by rho. That means simply Z1 by rho. What about tan alpha 2? Tan alpha 2 means you have to see this right angle triangle. Okay. You have to see this right angle triangle and alpha 2 is defined here. So what will get? Z2 minus 0 by rho, that means Z2 by rho. Similarly, tan alpha is equal to Z minus 0 by rho, that is Z by rho. But what is our observation is, as I said earlier, Z1 is fixed, Z2 is fixed, rho is fixed. So alpha 1 and alpha 2 will be fixed. Okay, alpha 1 and alpha 2 are constants. As Z is variable, alpha is also variable. Okay, so now coming to this equation. Here the integration is with respect to Z. Now we have to go to the variable alpha from the Z. For that, you can use this expression. Alpha and Z are available here. So Z is equal to rho tan alpha we can take. So I am taking now Z is equal to rho tan alpha, changing the variable from Z to alpha. So dz is equal to, I can write rho secant square alpha d alpha. When Z is equal to Z1, alpha is equal to alpha 1. When Z is equal to Z2, alpha will become alpha. Okay, when Z is equal to this Z1, actually what will happen? Tan alpha is equal to Z1 by rho. It is the formula for alpha 1. Okay, so you can able to write like that. So by making this variable change, the h bar expression will become like this. H bar is equal to I rho phi cap by 4 pi. Then integral alpha is equal to alpha 1 to alpha 2. And what is there here? dz. dz is nothing but rho secant square alpha d alpha by, what is that? Rho square plus z square is there. So z square means you can write a rho square tan square. So rho square if you take common and power 3 by 2 is there, rho cube you will get 1 plus tan square is secant square and 1 by 2 will be cancelled. So that secant cube alpha you will get. Then it is equal to, if you observe, this is one row, this is another row. So in the numerator rho square is there, in the denominator rho cube is there, so one row will come. And it is a secant square, it is secant cube. So 1 by secant, that means cos. Okay. So I by 4 pi rho will get. Rho square by rho cube means in the denominator we will get a rho. It is phi cap. Now here integration is to be done with respect to alpha, for 1 by secant means a cosine function, cosine alpha d alpha. So it is equal to I by 4 pi rho cos alpha, integration is sin alpha. If you substitute the limits, you will get sin alpha 2 minus sin alpha 1 into phi cap. This is the total h bar. Okay, so for the finite length conductor, h bar is given by I by 4 pi rho into sin alpha 2 minus sin alpha 1 into phi cap. So what is the observation for this particular thing? If you take finite length conductor, current carrying conductor like this, and I am taking current is going upwards. Okay, so if you are checking the direction of magnetic field intensity at this particular point P1, if you are checking the magnetic field intensity at point P2, if you are checking direction of this magnetic field intensity at point P3, and also this side also, that is P4, P5, P6. At all these points, that means around the conductor, if you want to measure the h bar, how it is there. Generally, phi cap means what? In the direction of the unit vector phi cap, this h bar is rotating. That means revolving around the conductor. Okay, revolving around the conductor you can able to take. That means here the direction of h bar can be understood easily by using the right hand thumb rule. You need to hold the conductor in your right arm. Then thumb indicates the current direction. Thumb is indicating the current direction. And how you are holding the conductor, holding of conductor using right hand in the direction of h bar. Okay, that means here your four fingers, if you hold the conductor by keeping your right hand thumb towards the current direction, your four fingers are going into the screen, into the screen. You can try this one, but here it is coming out of the screen, coming out of the screen, coming out of the screen. Cross circle is indicating going into the screen, dot circle is indicating coming out of the screen. Okay, so you will be having the circulating magnetic field intensity around the conductor like this. So here it is going into the screen. Sorry. So going into coming out, going into coming out, going into coming out, like this you can able to take. Okay, then it is for the finite length conductor situated from Z1 to Z2. For example, if it is infinite length conductor, it is extended up to minus infinity, Z2 is extended up to plus infinity. Then we have equations for tan alpha 1, that is given by Z1 by rho. Tan alpha 2 is Z2 by rho. So it will become minus infinity. That means alpha 1 is becoming minus 90 degrees. Tan alpha 2 will become infinity. That means alpha 2 will become plus 90 degrees. So h bar is equal to I by 4 pi rho sin 90 minus of sin of minus 90 in the direction of I cap is equal to I by 4 pi rho is 1 plus 1 2 we get. That means I by 2 pi rho to phi cap. This is for infinite length current carrying conductor. For the finite length current carrying conductor, we have this expression.